Hello everyone, my name is Conways. I am from class 16. Today I am going to present a working model on geometry which is going to prove that the area of the circle is pi r square where pi equal to 22 by 7 or 3.14. So now let us know about circle. A circle is a closed plane geometrical shape. It is a locus of a point moving around a fixed point at a fixed distance away from the point. The fixed distance from the point is called the radius of the circle. In real life, we can get many examples of the circle like a wheel, a pizza, a circular ground, etc. So now let us learn what are the terms used in the case of a circle. Now let us know about radius. The radius of the circle is the line which joins the center of the circle with the outer boundary. It is usually represented by the small r or the capital R. In the formula for area and circumference of a circle, radius plays an important role which we are going to learn later. Now let us know about the diameter. The diameter of the circle is the line which divides the circle into two equal parts. In an easier way, you can say that it's just a double of the radius of the circle. Therefore, diameter equal to twice the radius of the circle. If the radius of the circle is known to us, we can easily calculate the diameter, such as radius equal to half of the diameter of a circle. Now let us know about circumference of a circle. The circumference of the circle is the perimeter or the boundary of the circle which is equal to 2 pi r. I have attached a thread from one end of the semicircle to the other side. If I pull the thread like this, it is going to complete the circumference of the semicircle, that is pi r. Let us take a circle with radius r. This circle will be divided into 16 equal sectors and the sectors are arranged as shown. The area of the circle will be equal to that of the parallelogram shaped figure formed by the sectors cut out from the circle. Since the sectors have an equal area, each sector will also have an equal arc length. The colored sector will contribute to that of the circumference of the circle. So thus, area of a parallelogram equal to base into height, where base equal to circumference of the semicircle, that is pi r, and height equal to the radius of the circle, which is r. So area equal to pi r into r, which is equal to pi r square. Thank you for watching the video.
A warm hello to everyone. I am Sneha Chakraborty from class 6A and I am here today to introduce you to a very interesting and exciting mathematical concept known as data handling, which is a topic in statistics. With this chart we have here. Statistics is the science dealing with the collection, analysis, presentation and interpretation of data. The term data handling means the method of arranging haphazard data in an orderly, logical manner so that it becomes easy to understand the data without having its detailed analysis. Data is a collection of facts in the form of numerical figures to give some information. Here we are going to concentrate on three ways of data handling: frequency distribution table, pictograph and bar graph. I have taken an example of 35 students of class 6 and the raw data is the number of their family members. We first arrange the raw data in ascending order to get the average data, which can be converted into the frequency distribution table, where in the first column the 35 students are arranged in 6 groups depending upon the number of their family members. In the second column, against each observation, we mark a stroke called tally mark each time the observation occurs in the given data. To make the counting convenient, we write the tally marks in bunches of 5. For example, here 3 is repeated 4 times, so we write 4 in the form of tally marks. A frequency of data can be easily represented using tally marks. We write the frequency or the number of families in the third column. Now we move on to a pictograph. A pictograph is a presentation of data in the form of pictures. Here we are representing a table containing the different types of fruits preferred by 36 students in a class. As you can see, I have depicted a pictograph containing the different groups of students having the same choice of fruit. I have drawn 11 bananas, 9 apples, 10 mangoes and 6 pears according to the student's preference. Now we come to the final method of data handling known as bar graph, which is a graphical display of the data in the form of bars of different heights according to a scale. Here is a bar graph showing the number of students who prefer different activities in the vertical y-axis, where the scale is 1 unit height is equal to 5 students, and the preferred activities in the horizontal x-axis. Each bar has been extended to the respective markings representing the number of students. As you can see, the bar representing playing is the highest, from where we can understand that most of the students are interested in playing and the least in listening to music. These methods enable us to analyze the given data in a simple and easy way. Tally marks are most commonly used to represent the scoreboard in games and sports, whereas bar graphs are used in the measurement of rainfall, agricultural and industrial production. I hope you all have understood the concept and enjoyed the presentation. Thank you.
Hello everyone, and today I shall be discussing the Pythagoras theorem, one of the most important concepts of mathematics. Pythagoras of Samos was an ancient Ionian Greek philosopher and the eponymous founder of Pythagoreanism. In antiquity, Pythagoras was credited with many mathematical and scientific discoveries, which includes the most famous Pythagoras theorem. Now, what exactly is the Pythagoras theorem? Well, according to the Pythagoras theorem, in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. Putting it in a mathematical equation, we get c squared is equal to a squared plus b squared. I shall be discussing Bhaskara, the famous Indian mathematician's second proof of the Pythagoras theorem using the paper folding art of origami. Here we have obtained four congruent right-angled triangles with a small square inside it and all together contained in a large square. Now let us look at the mathematical proof of the Pythagoras theorem. Looking at this diagram in the chart, we can understand that the area of the large square is equal to the area of the small square plus the area of the four congruent right-angled triangles. Therefore, c squared is equal to a minus b whole squared plus 4 into half ab. On further simplification, we finally obtain a squared plus b squared. Therefore, c squared is equal to a squared plus b squared, which is exactly what the Pythagoras theorem states. Hence, we have successfully proved the Pythagoras theorem.
Hello everyone. Today, I, Hitash Sengupta from 7A shall explain how to get the value of pi to be approximately 3.14. My classmate Shantan Ghosh will navigate the presentation. This method of finding the value of pi was invented by Archimedes in 250 BC, a Greek mathematician, physicist, engineer, inventor, and astronomer. Here, we can see that a regular hexagon has been drawn inside the circle. The polygon is divided into 6 equilateral triangles. The thick black line divides the polygon into 12 equal parts. We can assume that the radius of the circle is r, which is equal to 1. Since the diameter of a circle is twice its radius, the diameter here is 2r, which is equal to 2. The line segment CB is being bisected by the thick black line. Therefore, line segment AC is equal to r by 2, which is equal to 0.5 or 1 by 2. Each side of this 12-sided polygon is marked by a red boundary. Now, consider the hexagon. In order to find the measurement of GC, we first need to find the measurement of HG. But in order to find HG, we first need to find the measurement of OH, which we will do by using the Pythagoras theorem. OH is equal to the square root of OC squared minus AC squared. The value of OH is observed as 0.866024. Thus, the value of HG, which is OC minus OH, is 0.133974. Again, by using the Pythagoras theorem, we find the measurement of GC as the square root of 8c squared plus 8g squared, which is equal to 0.5176381. Since it is a regular hexagon, number of sides is 6, so the perimeter is 6r, which is 6. We know that the circumference or perimeter of a circle is 2 pi r, so value of pi is perimeter by diameter. Here, the value of pi is 6 by 2, which is 3. As the number of sides of the polygon is increased to 12, 24, 48 and so on, the value of pi becomes more and more precise. In the shared table, it is noticed that after a certain point of time, 3.14 is getting repeated several times as the final value of pi, and hence we can assume that 3.14 is the closest approximation of the value of pi. Hope you all liked our presentation.
Hello, today I, Anusha Chaudhary of 7E, will walk you through two interesting ways of visualizing mathematical concepts. Shagnik Chaudhary will navigate through the presentation. What is the area of a circle? It is pi r square. But have you ever wondered why it is pi r square? In order to visualize this, let's take a circle. I fill the circle with concentric circles, one inside the other, to fill it up completely. Now let's take a single circle on the right. I cut this out and I get a straight line. Let me do the same with a set of concentric circles. I cut them up, open them and keep it on the right. The outermost circle will become the bottommost line and the other inner circles will come one line above the other with decreasing length. The circumference of the circle will be the length of the bottom line, that is 2 pi r, and the height will be the radius of the outermost circle, that is r. So area of the circle is equal to the area of this triangle, which is half into base into height. Here base is 2 pi r and height is r, so the area is pi r squared. Isn't this way of visualizing area of a circle using a triangle intriguing? Now let's move to our second method. We take a circle and cut it into 16 sectors using different diameters. Number them as 1, 2 up to 16. For ease of understanding, we will color the odd sectors blue and the even ones yellow. Let's take the first sector and keep it upright on the right. Then take the second sector and keep it upside down beside it. If I bring all of them and keep it on the right, we get a parallelogram which can be adjusted into a rectangle by shifting half of sector 1 from the left end to the right end. So what we can see is that the circumference of the circle has been divided into two equal parts. 1, 3 up to 15 in the bottom and 2, 4 up to 16 at the top. Each part makes up one length of the rectangle, making it equal to half of 2 pi r. The breadth is r, so the area of the circle will be the area of the rectangle, which is the product of length and breadth. That is half into 2 pi r into r, giving us pi r squared. So here we have visualized the area of a circle using a rectangle in a very easy way. Thank you for watching us.
Hope you enjoyed it. Thank you.
Good day everyone. Today we, the students of class 8, are going to present to you a project related to equating a solar eclipse.
A total solar eclipse might seem as a simple phenomenon, but you will be surprised to know that how mathematics, a part of our daily life, plays an important role in the formation of a total solar eclipse. A total solar eclipse is a phenomenon in which the Earth, Sun and the Moon come in a straight line and the Moon passes between the Earth and the Sun, thus blocking the Sun. So the people living in that area cannot see the Sun until the eclipse ends. We know that the diameter of the Sun is about 400 times larger than the diameter of the Moon. But the apparent size of the Moon will be larger than the apparent size of the Sun because the moon is nearer to the earth and the sun is far away from it, and thus the total solar eclipses will be possible if the distance to the sun from the earth is at least 400 times more than the distance to the moon from the earth. So, what is the actual math behind a total solar eclipse?
The distance to the sun from the earth ranges between 1.47 into 10 to the power 8 kilometers and 1.52 into 10 to the power 8 kilometers approximately, and the distance to the moon from the earth ranges between 3.6 into 10 to the power 5 kilometers and 4.06 into 10 to the power 5 kilometers respectively. Given these numbers, we can figure out that how much the apparent size of the sun gets reduced in comparison to the apparent size of the moon due to its greater distance from us.
When the sun is at its farthest point and the moon is at its point, the sun is 1.52 into 10 to the power 8 kilometer by 3.6 into 10 to the power 5 kilometer, or about 422 times further away from the earth than the moon. In other words, at that time, the factor of 400 difference between the diameter of the sun and the diameter of the moon, and the factor of 422 difference between the distances to each of them from the earth, conspired to make the apparent size of the sun and the apparent size of the moon nearly identical. So we see, as a result of a bit lucky math, we get to experience the wonder of total solar eclipse.
Now, is there any mathematical formula to predict the next total solar eclipse?
Yes, the formula to find the next solar eclipse is delta T is equal to 62.92 plus 0.32217 into T plus 0.005589 into T squared, where Y is equal to year plus month minus 0.5 by 12 and T is equal to Y minus 2000.
Hello everyone. We all know about the dynamic duo of Tom and Jerry. Today, on this board, we have created a problem based on a very lovable cartoon. Now, the question is, in how many ways can Tom reach Jerry? We have shown 3 points here. Now, you may think that there are only 3 ways by which Tom can reach Jerry. He can go from A, then to Jerry. He can go from C and then to Jerry. He can go to B and then to Jerry. But he could also go from C to A and then to Jerry. He could go from C to B and then to Jerry. He could go from A to C and then to Jerry, and this goes on. So you see, from 3 points only, we get so many ways by which Tom can reach Jerry. Amazing, isn't it? Now this problem was based on the topic we are dealing with today, permutation and combination.
In mathematics, the notion of permutation refers to the act of arranging all the elements of a set in the same order or sequence, or if the set is already ordered, rearranging its elements. Let us look at the formula to find out the permutations of n things taken r at a time. That is n factorial divided by n minus r factorial, where n is the total number of elements in a set and r is the number of selected objects. On the contrary, combination is the selection of the same members of a set where order is disregarded. Let us look at the formula to find out combinations of n things taken r at a time, which is equal to n factorial divided by r factorial into n minus r factorial, where n is the total number of elements in a set and r is the number of selected objects.
Thank you, Anurag. Now, to understand the concepts of permutation and combination better, we shall look at 2 daily life examples of permutation and combination. Now, let's look at a question on permutation. The password for a website consists of 4 digits and 2 letters. Now, there is a twist in the question. The letters A and Z are to be excluded and repetition of digits and letters are allowed. So, how many unique passwords can be created using the following rules? Over to Ayush.
Thank you, Vivan. Now we can break this problem down into 2 parts. First, we'll come to the numerical part. Now I've taken 4 boxes as there are 4 digits and the number of possibilities in each box is 10 because there are 10 digits, that is 0 to 9. Now I've taken the digits as 3, 2, 3, 1. Now 3 is repeated, as we know that we can repeat the alphabets and digits. So the total number of possibilities will be 10 into 10 into 10 into 10, that is 10,000. Now let us come to the alphabets. Now there are 24 possibilities in each box and there are 2 boxes as there are 2 alphabets. Now why 24 possibilities? A and Z are not used as we have said before, and therefore the number of possibilities are 26 minus 2, that is 24. So I have taken the alphabets as X and Y. Now the total number of possibilities are 24 into 24, that is 576. Now let us look at the total number of passwords possible. 576 into 10,000, that is 57,60,000. Isn't it amazing that so many such unique passwords are possible? Over to Vivan to explain the next.
Thank you, Ayush. That was truly a complex question. Now, we shall deal with something simpler, something which we all love, the world of cricket. So here the question states that there are 15 players in a team, out of which 4 are spinners, but one of them is injured. So in how many possible ways can the spinners be selected for the main team? So as the question states, there are 4 spinners, but one of them is injured. So it leaves us with only 3 possible ways in which the spinners can be selected for the team.
Thank you, Vivan. That was a lot to absorb, but I am sure that the easy to remember formulas will help us in calculating the figures conveniently. Now let us look at some of the formulas that we should always remember to make our calculations faster.
In our daily life, there are countless examples of permutation and combination, starting from the fields of communication network, molecular biology, cryptography, network security, to developing our phone numbers. The list is endless. Thus, we see mathematics can be found everywhere, from our books to computer architecture, from our schools to shopping malls. The beauty of the subject can be found in every sphere of our life. Thank you.
Conway's Game of Life is a cellular automaton devised by English mathematician John Conway. It is a zero-player game, meaning that its outcome depends entirely on its initial configuration. It is run by activating certain cells on an infinite 2D grid. The 8 cells contiguous with a given cell are called its neighbors. At the beginning, the player determines if each individual cell will be on or off. After initiation, the game proceeds independently of the player in a series of steps called generations. In each generation, a given cell is turned on or off, depending on certain factors which we will now specify. If a living cell has 2 or 3 living neighbors in the present generation, it will stay alive in the next generation. If a living cell has less than 2 living neighbors, it will die in the next generation. If a living cell has more than 3 living neighbors, it will die in the next generation. If a dead cell has exactly 3 living neighbors, it will come to life in the next generation. Otherwise, it will remain dead. The following example demonstrates all these rules at once. This cell is alive and has 2 living neighbors, so it will stay alive in the next generation. This cell is alive and has no living neighbors, so it will die. This cell is alive and has 4 living neighbors, so it will die. This cell is dead and has exactly 3 living neighbors, so it will come to life. This cell is dead and has no living neighbors, so it will remain dead. Several patterns in the game of life are classified according to their behavior over the generations. Still lifes are patterns which do not change with passing generations. Oscillators are patterns whose states repeat after a fixed number of generations. The number of generations it takes for an oscillator to return to its original state is known as its period. For example, the blinker is an oscillator with period 2. Spaceships are patterns which repeat their state after being translated through the grid in a fixed number of generations. The simplest example of a spaceship is the glider. Guns are patterns which have an oscillating component and which also generate spaceships after a fixed number of generations. The first gun to be discovered in the game of life was the Gosper glider gun. Though many patterns stabilize quite soon, some patterns dissipate into chaos and behave erratically for a long time before collapsing to a state consisting of stable patterns like those mentioned earlier. The R pentomino, which looks quite simple, only stabilizes by generation 1103, by which time it has a population of 116 active cells. The acorn is another unstable pattern. It only stabilizes by generation 5206. Even though the rules for the game of life are completely deterministic, it is impossible to predict whether an arbitrary starting pattern will die out or start oscillating or expand forever without simulating it directly. The following clips demonstrate the staggering complexity that can emerge from systems governed by such elementary rules.
Despite being a relatively simple mathematical model, the game of life has some of the most unexpected properties.
The game of life can be described as Turing-complete. With infinite memory and sufficient time, a Turing-complete system can be programmed to solve any computational problem.
Thus, computations of unfathomable complexity can be distilled into merely a grid of colored cells, the evolution of which is dictated by the simplest of rules.
It's the 5th century BCE, and Pythagoras is walking down a road. While passing by a blacksmith's shop, he notices something interesting. Listening carefully, he realizes that the different hammers striking the anvils make different sounds. Pythagoras decides to delve deeper into the matter and gets some startling results.
We all know Pythagoras as the one who said a squared plus b squared equals c squared. But how many of us know that he was the one who laid the foundation for the notes of the octave system for Western classical music?
As we all know, the pitch of musical notes is deeply interrelated with the concept of frequency of sound waves. Higher the frequency of the wave, greater is the pitch or shrillness of the sound. Upon investigation, Pythagoras concluded that the pitch of the musical note being produced by a particular hammer was independent of the magnitude of stroke or the place the anvil was hit. In fact, it depended solely upon the relative weights of the hammers used. He showed that the octave and the fifth, which correlate pairs of pitches of frequency ratio 2:1 and 3:2 respectively, corresponded to hammers of weights in almost the exact same ratios. This is true for all other chords. Based on several experiments using different musical instruments, he confirmed his observations.
The following is the pitch relation Pythagoras devised for the octave system. Interestingly, we still use almost the exact same system.
It is probably one of the cruelest ironies in music history that Ludwig van Beethoven, the composer of some of the most famous pieces of Western classical music, spent most of his time gradually going deaf. When he composed the famous piece playing in the background, the Moonlight Sonata, in 1801, he was mostly deaf. Then how did he create such soul-touching music? The answer: some mathematics and science.
One of the major motives of the sonata is a triad system containing the notes D, F sharp and A. The speciality of this triad is that it can be represented as a geometric progression using the following formula.
The graphs of A, F sharp and D when put together look like this. As we can see, in 0.042 by 2 pi seconds, the waves mostly undergo constructive interference. This is what is called consonance and is naturally pleasant to the ear.
An equally intriguing part is Beethoven's use of dissonance using the notes B and C. The waves of these notes mainly undergo destructive interference in the same time, and hence it sounds naturally unpleasant. These happen to be the same consonance and dissonance used by Pythagoras.
The genius of Beethoven lies in subtly contrasting consonance and dissonance, creating a masterpiece. Although it is not clear whether Beethoven was aware of the mathematics behind this, it is clear that he understood the workings of the underlying science.
During the Romantic period of Western classical music, roughly 1800 to 1900, after Beethoven, many other composers have clearly included mathematical entities in their compositions. In particular, Chopin and Debussy composed pieces in which important changes in the music occur around the bar numbers close to Fibonacci numbers.
In recent years, artificial intelligence has been employed to compose pieces of contemporary Western classical music. AI is even said to be set to finish Beethoven's 10th Symphony, for which Beethoven could only complete a few sketches of the first movement.
Can artificial intelligence, based primarily on mathematics and logic, create pieces as subtle and amazing as the great composers have in the past? Only time will tell.